Hello, my name is Antonio Rosales, and me and my partner, Hector Cardenas, are going to be presenting the work that we have done under the mentorship of Dr. Mustafa Al-Lail. This is our final presentation for our senior design project, developing a software tool for analyzing UML class diagrams. Our research rests within the context of model-driven engineering, which is a software engineering paradigm in which software designers use the unified modeling language to create platform-independent models. These platform-independent models are abstract representations of a given software system. Platform-independent models can then be transformed using a model transformation in order to produce platform-specific models. A code generator can then use these platform-specific models in order to produce production software code. Within the model-driven approach, these platform-specific models can then be used in conjunction with a code generator in order to produce production software code. Within the model-driven engineering approach, design faults in system models can propagate into code implementations. This can lead to bugs in software applications. Therefore, finding and fixing bugs in software code is necessary and can be very expensive if not done before it is implemented in software code. Therefore, design faults must be discovered as early as possible during the design stage. Although tools exist for validating and verifying the correctness of UML models, current UML-based analysis tools exhibit problems in their effectiveness, efficiency, and usability. Therefore, the objective of our research is to produce a UML-based analysis tool that is effective, efficient, and usable. As a result of our work, we have produced a working version of the tool. This is an overview of the functionality of the tool. Users must provide two inputs to analyze the system using our tool. First, an application design model, augmented with specification of operation behavior in the form of OCL pre and post conditions. This models the structure and behavior of the system. The second input is a behavioral requirement for the system, expressed as a temporal property in TOCL, an extension of OCL for temporal properties specification. The tool then checks the behavior of the input model and may or may not produce a counterexample within the given analysis configuration. A counterexample is simply an execution scenario of the system that violates the inputted temporal property and demonstrates that there is a design fault in the system. I will now let Hector speak more about the analysis approach used by our tool.
So now I'll go a little more into detail on how this tool actually works. So the first, it starts with a software designer who inputs an application design class model, which is a model that has classes which have their own attributes and operations and are associated in a certain way. In the first step, we take that class model and we transform it into a snapshot transition model, or STM, which allows us to represent it as a sequence of states and transitions. In the second step, we define a TOCL temporal property for this model. So let's say we have a restaurant model, which has classes like customer, cashier. Customers can have an attribute like money, an operation like pay for food. Well, a temporal property we might define for that is if customers pay for food, they should eventually receive that food. So that shows a property that we want to always be satisfied in a restaurant-like system. So a temporal property is a property related to time that a system must satisfy. In this second step, we allow designers to input them in TOCL, the temporal object constraint language, as it is more easy to define these properties in that language, but we can't actually analyze in TOCL. So in this step, we interpret them into OCL for our analysis. And that leads to the third step, which is feeding them to the use model validator, which is a tool that does the analysis of this model. The result of that is a counterexample if there are any flaws found. And in the fourth step, we take the counterexample and we extract a sequence diagram out of it, which shows a sequence of events that led to this error. We give that to the software designer so they can make the necessary changes to their model so that it works correctly. Now I'll talk about the objectives of this research. So like was mentioned earlier, the main objective is to develop a software tool for analyzing UML class diagrams, so mainly used diagram in model-driven engineering, and tailored towards UML designers. Some more specific objectives we've had as of late are to transform these counterexamples into sequence diagrams, that last step of the analysis overview from earlier. Also to test the core tool components to make sure that our tool is working correctly. Additionally, to integrate the pattern specification technique, which allow UML designers to more easily define temporal properties. To implement the search scope and search depth will make configuring analysis more easy. And also to improve the general GUI to make our tool easier to use and more presentable. So now I'll pass it back to Antonio to talk about our first objective.
Thank you, Hector. The first of our contributions that we're going to talk about is the implementation of an algorithm to extract UML sequence diagrams for snapshot transition model scenarios. The top of this slide demonstrates a snapshot transition model scenario. Our tool produces counterexamples in this format after performing analyses. However, for complex analyses, counterexamples in this STM format can be complicated and hard to comprehend. Therefore, we have implemented a transformation that extracts a UML sequence diagram, such as the one you can see at the bottom of the slide, from STM scenarios. This extraction allows users to more easily understand the counterexample scenario. The second contribution that we will talk about now is the formal testing of core model transformations in our tool. If you recall, our analysis approach introduces two model transformations. First, a transformation of a UML class diagram into a snapshot transition model. And second, a transformation of a TOCL temporal property into an OCL constraint. We have implemented these two transformations using software code. And so in order to ensure the reliability and correctness of our implementations, we must test both implementations using a formal transformation testing methodology. The first step in this testing methodology was to create a set of test cases. These test cases were generated using classifying terms. Classifying terms are a technique used by the testing approach that increase the diversity and effectiveness of the test cases. The second step in testing is defining transformation contracts. These contracts specify the intended behavior of our transformation. The set of generated test cases can then be transformed, and the models produced by the transformation can be checked to see if they satisfy the transformation contracts that we defined. This is a figure that shows a test case being validated for the class diagram to STM transformation. The class diagrams window in the middle of the slide displays 4 true values. This means that the contracts for this transformation are being satisfied. Now I'll let Hector show a test case for the next transformation.
Thank you. Similarly, for the TOCL to OCL transformation, we use the same methodology to test it. So here you can see an example of the testing for the universal pattern in global scope. Matt Dwyer, a professor of computer science and software engineering, found that temporal properties could be grouped into different patterns. Dr. Al-Lail, our mentor, furthered this by creating TOCL temporal property patterns. And we use that for our test cases. So you can see the testing of one, a TOCL representation on the left and OCL on the right. And you can see that it's satisfying its tract. Now I'll talk about the pattern specification technique. So UML designers should be familiar with OCL, as it is often used to create pre and post conditions and variants, different very common things in creating software models. But they might not be familiar with TOCL, the temporal object constraint language. Although it extends OCL, it introduces new structures that may not be familiar. Thus, to make the process of defining temporal properties in TOCL more easy, we introduce a pattern specification technique. This involves using the patterns I mentioned earlier to create these properties and using them as templates. So here you can see a window of one of these specification patterns. You can see a short description, an example, an explanation, and instructions on how to use these patterns. And on the right, all you have to do is input in those text boxes the necessary piece of information or data necessary. Next, I'll talk about the search scope and search depth. So configuring analysis can be a difficult process. The use model validator, which we use for the analysis, requires many different inputs. As you can see here, you must specify the min and max object quantity for each class, also for each association of each class. And this also uses the snapshot transition model, or STM, which we don't want users to have to deal with at all. So instead, we implement the structures of search scope and search depth, which allow designers to more easily configure their analysis. The search scope basically defines the max amount of object that can occur in each snapshot or each state. And the search depth is the max amount of transitions that can be used when producing a counter example. Next, I'll talk about the challenges we faced. First, the formal testing of the TOCL to OCL transformation was a little difficult as the meta models for each are fairly large, and thus it's hard to be consistent when defining each. However, to attack that, we just were a little more thorough, and that helped us when doing this testing. Additionally, approving the tool GUI was a little difficult since we created a plugin which uses use. So to improve our plugin, we had to understand use very well. So to attack that, we had to look into the files of use and greatly understand that. Next, I'll talk about the conclusion. So to reiterate our objective, we want to develop a software tool for analyzing UML class diagrams and tailor it towards UML designers. And to further go towards that, we did some formal testing of transformations. We integrated the STM to sequence diagram transformation for that fourth step of the analysis overview to give to software designers. We included the pattern specification technique to make specifying temporal properties easier. And we implemented the search scope and depth constructs to make configuring analyses easier. In addition to that, our future work involves tool evaluation, which will consider the efficiency, efficacy, and usability of our tool. We want to compare against other tools in this field and see how ours matches up to them. Using this, we want to also improve the GUI to make our tool more usable and more presentable. We also hope to do some code generation. The main and primary focus of our tool is to analyze UML class diagrams, which, if no faults are found, are then ready to be transformed into code. So might as well allow users to use our tool for its code generation and make it easier on the UML designer. Additionally, we want to improve the optimization technique, which basically means improve the efficiency of our tool, especially time-wise, so that our analysis works faster. Also, we hope to continue this work in graduate school at Texas A&M and hopefully include this as part of our master's thesis. Next, I also want to mention that we submitted this work to ICSE, the IEEE/ACM Conference on Software Engineering, for the 2023 demo track, which is for tool demonstrations. And now we'll show you this video of our demo that we submitted. Lastly, these are our references. Thank you for listening to our presentation.